This video is on the thin lens equation, and the thin lens equation is developed by looking at an image. So in this case we have a light ray coming in, so that would be the yellow line here, hits a converging lens, which is really a double convex lens, so it's curved on both sides. That when the light passes through there, you get refraction, and then we get the image on the opposite side. Right, so this would be our object here, and our image on the secondary principal axis side. Something that you've done in the lab, you've looked at that, in terms of ray diagrams. So we know that we can figure out where the image is and the size of the image by using ray diagrams. What the thin lens equation does is now looks at this setup here and allows you to be able to calculate mathematically the size of the image, size of the object, and an extension of that would be the magnification of an object. This is all based on similar triangles. So the similar triangles that we would be concerned with is, you would look at, say, this triangle here. That triangle is similar to the triangle that's right next to it. So remember, though this angle and this angle are going to be the same, that means proportionally then this side here and this side here are also going to be proportional. The distance here along the base of the triangle, both of those are going to be proportional as well. And those are all just properties of similar triangles. So the equation that I'm eventually going to show you is based on those similar properties. So we know that the sides of those triangles are proportional, and we can use that proportionality constant to develop an equation. Now, I am not going to go through every little step in how that equation is developed. What you really need to know is that it's based on this setup, right? So a ray of light that's going through a converging lens and also a diverging lens, which is something that we'll talk about later on. But they are going through a lens, and they're going to produce an image, a real image on one side, or it could be possible that they produce a virtual image, which is an image that's going to be on the same side as the object. Now, you have to define the parts of this diagram, so you could be able to link the parts to the equation that I'm going to show you next. So the first area is this distance here, and this is going to be called the distance of the object, and the distance of the object is from the center of your lens to where your object's located on the principal axis. So that's called dO, or d subscript O, for the distance of the object. Then we have on the other side, we can mark from, again, the center of the lens to the image. This is going to be referred to as DI, and that's the distance of the image from the center of the lens. So remember, everything's based on the center of that lens, and then we move out from there, so to either side. The other area that we're concerned with, which is something that you looked at in the lab and when you drew diagrams, is your focal length. So every lens has a specific focal length, and that focal length will dictate where that image is located in accordance to where the object is located on the primary side. All right, so we're going to use that information now and look at the next slide. The next slide summarizes everything that we've been talking about. So the equation that we came up with, and again, this is based on the relationship between the sides of similar triangles. So knowing that they're proportional, we came up with the equation that if we have 1 over the distance of the object plus 1 over the distance of the image is equivalent to 1 over the focal length. So I've just defined that down here. So again, this is the distance of the object to the lens. Again, that's the center of the lens, usually measured in centimeters. Then we have the distance of the image. So again, the subscript is representing image. And again, the distance of the image to the center of the lens. And again, that's measured in centimeters. Focal length. Again, that focal length is either given to you on the lens, like the package will tell you what the focal length is, or you can look at a distant object like we did with a light bulb to determine the focal length of that particular lens. Now, that thin lens equation comes with some conditions. And this is where this is really important to pay attention to when you start doing equations or word problems using that thin lens equation. So, first thing is your distance of your object. The value that distance is will always be positive. All right, and that's important. Once you get that set up, whatever number or length that distance of the object is, that number will always be positive. However, the distance of the image is different. If it's a real image, which means that if we had a lens here, and this is our principal axis, and this is our object, if the ray of light goes through and then forms an image over here, then this is a real image, right? It's gone through the lens, formed a real image. It's usually inverted, but you would be able to capture that on a screen. If that's the case, if it's a real image, then that is positive. So when you read a word problem, that's important to remember. Right? So if it's a real image, you've looked at those ray diagrams, you know what's going to be real and what's going to be a virtual image, then that has to be a positive. Then, if it is a virtual image, which means that it actually ends up on this side, back on the primary side, if it's a virtual image, that number is negative. Now the questions won't tell you whether it's negative or positive. You have to interpret that by understanding whether it's a virtual image or a real image. And that is important to be careful when you write down your given, that you understand that what is real and what is virtual. Focal length is also important. If you're looking at a converging lens, which is a lens that we've been using in the lab, so it's really kind of bubbled on both sides, which is really called a double convex lens, then that focal length is positive. If it is a diverging lens, which means it dips in the middle, so it's really a double concave lens, then we would say that it is negative. So we're going to use this information right now in word problems. So we're going to use the thin lens equation. You have to interpret your distance of your object, distance of your image, and your focal length depending on whether the object is real or virtual, and whether you're dealing with a converging or diverging lens. Alright, so we're going to do a couple practice problems. So you want to turn to page 566 in your textbook, and I would actually just pause the video right now, and I would read through the question and think about what the terminology is and what kind of setup it would be in terms of that particular equation that's going to use the thin lens equation. So I'll read it. So question 1 is, a converging lens has a focal length of 23 centimeters. A frog is 32 centimeters from the lens. Use the thin lens equation to calculate where the image of the frog will be located. So it tells you the focal length. It is a converging lens, so this is positive, right? Because converging lenses are positive, diverging lenses would be negative. the distance of the object is 32 centimeters, right? 32 centimeters produces an image that is going to be on this side of the setup, which means it's going to be real. And because it's real, then this is also positive. So when you read through the question, that's kind of some key components here. So you have to know the focal length, and you have to know whether it's a converging or diverging lens, and you need to know the distance of the object, which wherever that position is, it all will determine where it's going to be located on the real side. So again, that goes back to ray diagrams and just understanding the location of the image in respect to where that object starts in that ray diagram. So if you need to go back and look at those different diagrams and get familiar where the image is going to end up being located in each one of those situations. And that will help you predict whether it's going to be positive or negative. Once you've set that up, then you're going to then start off with your thin lens equation. You're going to plug in your information. So in this case, we have our distance of our object and we have our focal length. This is what we're trying to find. We're trying to find the distance of the image. Again, that's the distance of the image from the middle of the lens to where it's located on the secondary side of the principal axis. So you're going to rearrange that, so you're going to end up with a fraction. So it's going to be 1 over 23 subtract 1 over 32. To solve that, what you want to do is you want to take 1 and divide it by 23, and that's going to give you a decimal. And then you're going to subtract that, or you're going to subtract the 1 over 32, you're going to change that to a decimal. So both of these, it's going to be 1 divided by 23, 1 divided by 32, which is going to give you 2 decimals. You're going to subtract them, and that will give you this final decimal. Now, on this side, it is an inverse relationship. So we have a 1 over distance of the image. To make it di, you got to reciprocate it. Right? So you're going to invert the fraction, so you're going to end up with di. When you do that, you have to do the same to the other side. So what you're doing is you're taking this decimal and you're putting it to the -1, or you're really taking 1 and dividing it by 0.0122. Then this gives you your answer. So the image will be 82 centimeters from the center of the converging lens. Now, it is a lot to think about, right? So you do want to go through this. You want to make sure, you want to understand why I'm choosing positives for these numbers. And you want to make sure you understand mathematically why when I invert the 1 over di to get to the di, why I'm dividing it into 1. Right, so you want to review that, and if you've got questions about that, we will address that in class on Thursday. But you do want to take a look at this and make sure you're understanding where this information is coming, how it relates to the diagram. Second question, so again, that's on page 566. So again, if you have your textbook, I would pause it, read it, kind of get a feel for what the information is telling us. But as you read through the question, it states a pencil is located 53 centimeters from a diverging lens. Okay, indicates a diverging lens. Then we know that our di needs to be -18 centimeters. Because it's going to end up being a virtual image. Right, so that's going to be negative. Right, because it goes on, it says an upright virtual image of the pencil is observed 18 centimeters from the lens. So that's, again, that's -18. We also know our answer is going to be a negative, because when it is a diverging lens, we know that the focal length is negative. So again, we're going to plug this information into our thin lens equation. So we get 1 over 53, 1 over 18 equals 1 over f. we're doing the same process. We're going to take 1 divided by 53, 1 divided by 18. We're finding the difference between those numbers, which is going to end up being a negative 0.0367. Then we take this, right? We're going to find the reciprocal. We got to reciprocate the other side, because whatever we do to one side, we have to do the other. That's why I have a negative 1 here. That really means that you're taking 1 and dividing it by 0.0367, or you're dividing this decimal into 1. That will then give you a focal length of negative 27 centimeters. And again, that negative indicates that we're dealing with a diverging lens. Right? So negatives and positives are extremely important in the thin lens equation, which actually is a good lesson, or a good process to start thinking about, because if you ever do take grade 11 physics, that is extremely important. Negative and positives and how they work into equations really help you predict the outcome of different events in physics. And again, optics is no different in this case. Now, from that equation, because again we're dealing with ratios, we can come up with a magnification, so we can figure out the height of an object and height of an image. So again, this is all based on similar triangles. So we're kind of cutting corners here. We're jumping from similar triangles to that actual relationship. So if I wanted to find the magnification, or the height of my image, or the height of my object, knowing the magnification, then the ratio is height of the image over the height of the object, or you can remember it as hi-ho. If you're going to look at the distance of the image and the distance of the object, again, it's that's the ratio, image over the object, or dido. Right? So you can kind of think of those, try to kind of remember what's happening in that magnification. Again, we have conventions for magnification. So again, when the height of the object and the height of the image, it is positive when they are upwards from the principal axis. And what that means is, if this is your principal axis, your image is in an upright direction. When they are downward, so when the image is inverted or down from the principal axis, then it is negative. So again, slight differences, but make huge differences in your calculation. So you need to know when an object is upwards and when it's downwards. So then you need to make sure you include that into your information and you're given in your question. Magnification, so the big M, which is that's what that represents. So magnification equation, that's what the M stands for. It's positive when it's an upright image. Right? So the image on the other side, or it could be a virtual image. So we would say that's a positive, so that value needs to be positive. If it's an inverted image, then it's negative. So again, reading the question carefully helps you correctly put the information into your equation. So, if you look at question 5 on page 566, again, I would stop, read the question just to get the information down, see where I'm getting my negatives and positives from. But again, number 5, a vase of a height of 12 centimeters is placed in front of a converging lens. An inverted image of height 35 centimeters is noticed on the other side of the lens. So, object, upright, 12 centimeters. The image is inverted, so it is negative. Again, if you read the question, it doesn't tell you it's negative. That's what you have to interpret from the question because of the way the image is oriented. So in this case, it's inverted. When it's inverted, it's a negative. So we're trying to find our magnification. Magnification is hi-ho, so hi over HO. We are going to then plug in our information, so we know the height of our image is negative 35. We're going to divide that by 12. The centimeters get crossed out, so there's no unit for magnification, we just say it's just a multiple. So in this case, this is a negative 2.9 times, right? That's just the amount of magnification that's happening in the object. Now, this, if you drew this out and if you look at the particular diagram, you would realize that this is going to be a real image, right? It would be able to be captured on the screen. So that summarizes a lot of the information about the thin lens equation. You definitely want to review this video again and just get the idea of the equation. Again, the importance of knowing what a positive and negative. And on Thursday, you'll get a worksheet and you'll have time in class to start working through that information, ask questions, and clarify any ideas about the video itself. Later on, probably not till tomorrow, you'll get an information video about diverging lenses and also convex mirrors.